Ever feel like your computer is juggling a million things at once?
Well, yeah. I mean, it kind of is.
Today, we're diving into the world of CPU scheduling,
Uh-huh.
the system that determines which of your computer programs gets attention from the CPU and
Well,
when. It's like a super efficient traffic cop directing the flow of tasks,
yep.
making sure everything runs smoothly.
That's right. And efficient CPU scheduling is about more than just speed. It impacts everything from how quickly your applications respond
Okay.
to how well your system handles multiple users or even complex tasks like gaming.
Right.
It's a crucial part of what makes your computer experience seamless.
And get this, we'll be exploring algorithms with names like round robin
Oh, yeah.
and shortest job first, which honestly sound like they belong in a sci-fi movie.
I know, right?
We've got a stack of research and code examples to break down so
Yeah.
you can really understand what's happening under the hood.
What's fascinating is that understanding these concepts can actually help you make informed decisions about your own tech, whether it's troubleshooting a slow computer or choosing a new operating system.
Uh-huh.
Knowing a bit about CPU scheduling can give you a real advantage.
Okay, let's unpack this, starting with round robin scheduling.
Okay.
Our source, the round robin scheduling document, explains that this algorithm is all about fairness.
Right.
Each process gets a fixed amount of time on the CPU,
Uh-huh.
called a time quantum, before being sent to the back of the line.
It's like a game of musical chairs for your computer programs.
Uh-huh, okay.
This ensures that no single process hogs the CPU,
Right.
preventing those frustrating slowdowns when your computer seems to freeze up.
Now, our source also provides some C code that shows how this works in practice.
Yes.
It uses a simple queue to keep track of the waiting processes.
Uh-huh.
Can you walk us through that? I'm curious to see how the code actually implements this musical chairs concept.
Absolutely. So the code sets a specific time quantum,
Okay.
let's say 2 seconds.
All right.
Then it goes through the queue of processes,
Mhm.
giving each one 2 seconds of CPU time before moving it to the back of the queue.
So if a process needs more than 2 seconds to complete its task, it gets interrupted
Yes.
and has to wait its turn again.
Precisely. And that's the key to round robin, preemption.
Okay.
Even if a process has a longer task, it gets divided into these smaller chunks,
Uh-huh.
ensuring that other processes get their fair share of CPU time.
Right?
And the output of the code actually shows you the exact order in which processes get completed,
Okay.
along with metrics like waiting time and turnaround time.
That's pretty neat. But what about situations where processes arrive at different times?
Oh yeah, good point.
Wouldn't that mess up the queue?
Great question. Our source material also describes a more complex round-robin implementation using a linked list.
Oh, wow.
This allows the scheduler to dynamically add new processes to the queue
Okay.
as they arrive, ensuring fairness even in a more dynamic environment.
So it's like the traffic cop adjusting the traffic lights to accommodate cars coming from different directions.
Exactly. It's about maintaining a smooth flow, even when things get unpredictable.
Makes sense.
But round robin isn't the only scheduling algorithm out there.
Right.
Let's look at first come, first serve,
Yeah.
SCFS, and shortest job first, SJF,
Okay.
which are discussed in CPU scheduling and operating systems.
All right. So FCFS sounds pretty straightforward. Like a polite line at the bakery.
Yeah.
Whoever arrives first gets served first.
Exactly.
Simple, right.
Yes, but just like that bakery line,
Hmm.
FCFS has its downsides.
Oh.
Imagine getting stuck behind someone ordering a complex multi-tiered cake
Oh, no.
when all you want is a simple loaf of bread.
Right.
A long process can hold up shorter ones,
Uh-huh.
creating delays.
So in that scenario, SJF would be like the bakery prioritizing those quick bread orders to keep the line moving.
Exactly. SJF focuses on efficiency by prioritizing processes with the shortest execution times known as burst times.
Okay.
It aims to minimize the overall waiting time for all processes,
Uh-huh.
making the system feel more responsive.
Sounds great, but I'm guessing there's a catch.
Oh.
If it's always prioritizing the shortest jobs, what happens to those longer, more complex tasks?
That's where the concept of starvation comes in. If a continuous stream of short tasks arrives,
Yeah.
those longer processes might never get a chance to run.
Yeah?
It's like that complex cake order never getting fulfilled
Oh, no.
because the baker keeps getting distracted by simpler requests.
So there's always a trade-off.
Right.
FCFS might be fair, but potentially inefficient,
Uh-huh.
while SGF is efficient but carries the risk of starvation.
That's the challenge with CPU scheduling, finding the right balance. And it's fascinating to see how these theoretical concepts are implemented in code.
Yeah.
The source material provides C code examples for both FCFS and SJF,
Uh-huh.
highlighting how they manage process queues differently.
It's amazing to see how a few lines of code can have such a significant impact on the overall performance and user experience. It's like we're seeing the puppet master behind the scenes.
And it gets even more interesting when we start assigning priority levels to different processes, which we'll explore next with priority scheduling.
Okay, this is where I feel like we're getting into the VIP section of the CPU nightclub.
Ah,
Some processes get preferential treatment?
yes.
Tell me more. So we're talking priority scheduling, and our source priority scheduling lays it all out.
Uh-huh.
It's like giving some processes a fast pass at an amusement park.
Yeah, like a VIP ticket.
But how do we decide which processes get to skip the line?
Well, each process is assigned a priority level,
Okay.
and the scheduler uses this to decide who gets access to the CPU first.
Right.
Higher priority processes get preferential treatment, ensuring critical tasks get completed quickly.
But wouldn't that lead to lower priority processes being constantly ignored? They're stuck in a never-ending queue?
That's a risk, and it's a key consideration in priority scheduling.
Okay.
Designers need to carefully balance priorities
Uh-huh.
to prevent starvation of lower priority processes. Sometimes techniques like aging are used,
Okay.
where the priority of a process increases the longer it waits,
Interesting.
ensuring it eventually gets its turn.
That makes sense. It's like recognizing that even those waiting patiently in the regular line deserve a chance to ride the roller coaster eventually.
Right.
But how does priority scheduling actually work in practice? Are we talking about constant interruptions and chaos?
Well, there are two main flavors of priority scheduling:
Okay.
preemptive and non-preemptive. Think of it like this. You're in a meeting and suddenly your phone rings. With preemptive scheduling, that ringing phone is a high priority process that interrupts your meeting, a lower priority process.
I see.
But with non-preemptive scheduling, you let the meeting finish before answering the call, no matter how important it might be.
So preemptive priority scheduling is all about immediate action,
Right.
while non-preemptive is more about maintaining order.
Exactly. The choice between them depends on the specific needs of the system. In real-time systems where responsiveness is critical, preemptive scheduling reigns supreme. Okay.
Imagine a system controlling medical equipment. You wouldn't want a critical task delayed because a less important one was running.
That's a great point. Our source provides some insightful examples that demonstrate how both preemptive and non-preemptive priority scheduling affect waiting times and turnaround times for different processes. It's like seeing those two different phone scenarios play out and how they impact everyone involved.
And those examples highlight a crucial challenge with priority scheduling: priority inversion.
Uh-oh.
Imagine that urgent phone call being delayed because the person you need to talk to is stuck in a less important meeting that they can't interrupt. Similarly, in a computer system, a low priority process might hold a resource needed by a high priority process, causing unexpected delays.
That's a fascinating problem.
Yeah.
It's like the VIP getting stuck in traffic behind a slow-moving truck. So designers need to be very careful about not just assigning priorities, but also anticipating potential conflicts and dependencies between processes. Absolutely. And sometimes they use techniques like priority inheritance, where the low priority process temporarily inherits the priority of the high priority process that's waiting for the resource, preventing these bottlenecks.
It's like giving that truck a temporary police escort to clear the path for the VIP.
That's a clever solution. So priority scheduling isn't just about assigning a number to a process. It's about carefully orchestrating the entire system to ensure critical tasks get the attention they deserve without causing chaos or unfair delays.
You got it. It's a delicate dance between efficiency, responsiveness, and fairness, and it's fascinating to see how different operating systems tackle this challenge. But now let's switch gears from the CPU to another critical part of the computer: memory.
Okay.
Specifically, we're going to dive into the world of page replacement algorithms.
Okay, we're moving from the bustling city of the CPU to the vast library of memory. I'm intrigued. Tell me, what are these page replacement algorithms all about?
Imagine your computer's memory as a giant library with shelves full of books.
Each book represents a page of information. When you open a program or access a file, you're essentially requesting a specific book from the library. But what happens when the library is full and you need to add a new book? That's where page replacement algorithms come in.
So it's like needing to make space on your bookshelf for a new book by deciding which one to donate.
Exactly. But instead of making random decisions, computers use clever algorithms to choose which pages to evict from memory when it gets full. And just like with CPU scheduling, there are several different approaches, each with its own trade-offs.
Our source page replacement in operating systems covers three main algorithms: FIFO, LRU, and LFU. I'm curious to see how these play out in the context of our library analogy.
Well, FIFO, or first in, first out, is the simplest. It's like organizing your bookshelf based purely on when you bought each book.
Oh, okay.
The oldest books get donated first, regardless of how often you read them.
So FIFO is all about seniority.
Yeah,
The first page to enter memory is the first to go when space is needed.
precisely. It's easy to implement, but not always the most efficient. You might end up donating a book you still refer to regularly, just because it's been on your shelf the longest.
That sounds a bit like a random purge. What about LRU, which stands for least recently used? Is it more about considering actual usage patterns?
Exactly. LRU is like keeping your favorite books on a special shelf within easy reach. The books you haven't touched in a while get moved to a less accessible area or even donated.
I see.
Similarly, LRU keeps track of which pages have been used recently and prioritizes replacing those that haven't been accessed in a while.
So it's assuming that if you haven't read a book recently, you're less likely to need it soon.
Precisely. It reflects the idea that we tend to access recently used information more frequently. Of course, it adds a bit of complexity because the system needs to keep track of page usage history,
Right.
but it often leads to better performance.
And then we have LFU, which stands for least frequently used. Is this like those books you bought with good intentions but only read once, if at all?
That's a great analogy. LFU focuses on long-term usage patterns.
Okay.
It keeps track of how often each page is accessed and prioritizes replacing those that are used less frequently. It's like realizing you haven't touched that cookbook in years and deciding it's time to donate it, even if you bought it more recently than other books you use regularly.
So FIFO is simple but potentially inefficient. LRU considers recent usage, and LFU looks at long-term patterns. It seems like each algorithm has its own strengths and weaknesses.
Absolutely. And our source material provides some excellent examples to illustrate how each algorithm works step by step. It shows how they handle a sequence of page requests, which pages get replaced, and how many page faults occur.
Okay.
Those moments when the system can't find the requested page in memory and has to retrieve it from secondary storage.
That's like going to the library and finding that your book has been moved to the archives. It takes extra time to retrieve it.
Yeah.
So choosing the right page replacement algorithm can significantly impact a computer's performance.
Exactly. And it's fascinating to see how these seemingly simple decisions about which books to keep and which to donate can have such a profound effect on the overall efficiency of the system.
But you mentioned earlier that even simple algorithms can have surprising quirks. Is there anything we should watch out for with these page replacement algorithms?
Well, there's a curious phenomenon known as Bilaty's anomaly, which primarily affects the FIFO algorithm.
Okay, anomaly sounds ominous. What is this Bilaty's anomaly all about?
You'd think that having more memory or more space in our library analogy would always lead to better performance, right?
What? Yeah.
More shelves mean more books within easy reach.
Right.
But Bilaty's anomaly shows that in some cases, using the FIFO algorithm with more memory space can actually lead to more page faults.
Wait, so having more space can actually make things worse? How is that even possible?
It's counterintuitive, I know. It has to do with the specific order of page requests and how FIFO manages its queue. Imagine adding more shelves to your library, but because of the way you're organized, you end up needing to retrieve books from storage more often.
Right?
It's a reminder that intuition doesn't always apply in computer science, and careful analysis is crucial.
That's mind-blowing. It's like expanding your library and somehow ending up with less accessible books.
Exactly. Bilaty's anomaly highlights the importance of choosing the right algorithm based on the specific characteristics of the workload and the system's memory capacity.
So it's not just about having enough space, it's about managing that space effectively. And these page replacement algorithms, although invisible to most users, are playing a crucial role in that management.
Absolutely. They're constantly working behind the scenes to ensure that the information you need is readily available. And understanding how they work can help you appreciate the complexity and ingenuity of these systems that we often take for granted.
I have to admit, this deep dive is making me see my computer in a whole new light. It's like we've peeled back the layers and revealed the intricate machinery that keeps everything running smoothly.
That's the power of knowledge.
Yeah.
And even if you don't remember all the technical details, understanding the basic principles of CPU scheduling and page replacement algorithms can give you a deeper appreciation for how computers work,
Great.
and even help you troubleshoot issues or make informed decisions about your tech.
It's like we've gained a superpower. The ability to see the invisible forces shaping our digital world.
Yeah.
But it's not just about computers, is it? These concepts of scheduling, prioritization, and resource management, they seem to apply to so many aspects of our lives.
You're absolutely right. Think about project management, time management, even decision-making in our daily lives.
Uh-huh.
We're constantly juggling tasks, prioritizing goals, and allocating
It's
resources.
like we're all running our own internal operating systems, constantly making choices about what to focus on and when.
Exactly. And the more we understand these principles, the better we can manage our own systems, whether it's our work, our time, or our energy.
So what does this all mean for us as users, both in the digital world and in our everyday lives? How can we use this knowledge to make our computers run more smoothly and perhaps even make better decisions in general?
Well, when it comes to your computer being mindful of how many programs you have open at once is a good start.
Okay,
Remember, the CPU can only handle so much at a time,
right.
and juggling too many tasks can lead to those slowdowns we talked about earlier.
It's like trying to read multiple books at the same time. Your attention gets divided, and you might not fully absorb any of them.
Exactly. And when it comes to storage, think about those page replacement algorithms.
Okay.
If your computer is feeling sluggish, it might be spending too much time swapping pages in and out of memory.
So just like decluttering our physical spaces can improve our focus and productivity, decluttering our digital spaces can help our computers run more smoothly.
Precisely. Deleting unnecessary files, organizing your data, and closing unused applications can free up resources and allow those page replacement algorithms to work more effectively.
So it's not just about having enough storage space, it's also about how that space is managed. And these algorithms are constantly working behind the scenes to optimize that management, but we can help them out by keeping things tidy.
It's amazing how these seemingly technical concepts can have such practical applications in our daily lives.
It really is.
Who knew that understanding how a computer manages its to-do list could help us be more efficient with our own?
Right. It's all about recognizing those underlying patterns and principles. And this deep dive has only scratched the surface of CPU scheduling and page replacement algorithms.
Yeah.
There's so much more to explore, from more advanced algorithms to the specific ways different operating systems implement these concepts.
It's like we've opened a door to a whole new world, and I'm eager to see what else is out there. But even with this glimpse, I feel like I've gained valuable insights.
I'm definitely going to be more mindful of how many programs I have running at once.
Good idea. And perhaps you'll start to see those invisible systems at play in other areas of your life as well. How does your brain prioritize tasks?
Oh, wow.
What are your personal page replacement algorithms when it comes to making decisions or managing your time?
There are some really thought-provoking questions. It seems like this deep dive hasn't just been about understanding computers, it's been about understanding ourselves as well.
That's the beauty of knowledge.
Yeah.
It often transcends boundaries and leads us to unexpected connections. And who knows, maybe this exploration will inspire you to delve even deeper into the world of computer science, or even apply these principles to other areas of your life.
I have a feeling this is just the beginning of a much larger journey of discovery. Thank you so much for guiding us through this fascinating world of CPU scheduling and page replacement algorithms.
You're welcome.
It's been an incredible deep dive.
The pleasure was all mine. And remember, the more we understand the systems around us, both digital and in our own lives, the more empowered we become to navigate them effectively and make informed choices. Happy exploring.